Hello everyone, today let's take a look at QP150, a very hard, basically uniform distribution problem where we have x1 all the way up to xn as a sequence of independent uniform 0 to 1 random variables. We define n to be the first integer such that their sum basically exceeds this fixed constant z, where z is basically between 0 and 1. So it's asking us, what is the expected value of n as a function of x? Basically what we're saying here, if I have my number line between 0 and 1, I'm going to fix some constant z between 0 and 1, and then I'm going to take basically my uniform 0 to 1 random variables. Maybe my x1 is right here, and then I'm going to sum them up. I'm going to keep summing them up, so maybe my x1 plus x2 is right here. And then I keep going, maybe my x1 plus x2 plus x3 is right here, and then I'm going to keep summing them up until eventually I'm going to have something like this, where I have x1 plus x2 plus x3 plus x4, and then that's going to be greater than z. And at that point, right, n equals 4 in this case, because we're summing up 4 random variables. So this was the point right here. We had to take 4 random variables to get a value basically bigger than z. And we're saying, what is the expected value of basically that number that we need to exceed that threshold? So n is basically the number of uniform 0 to 1s needed to exceed z when they're summed up, and we're trying to find the expected value of n. So n is a discrete random variable because it is a number. It's either going to be 1, 2, 3, 4, 5, whatever, some type of number. It's going to take values basically between basically 1 and infinity. And if we were to use the normal expected value formula, right, k times the probability that n equals k, well, you'll notice that this will get pretty clunky. So instead, just by realizing that n is basically representing a stopping time, it's going to be a lot simpler to think about it in terms of basically the tail sum form of finding the expected value, right? It's going to be a lot easier to calculate that way. So instead, let's just have k go from 0 to infinity and calculate the probability that n is greater than k, and then sum that all up, and then that'll give us the expected value of n. We proved this tail sum works in QP122, and again, because we're dealing with a stopping time, tail sum will be easier. Now, just like with all of our problems, let's just start working through the first few cases. So what is the probability that n is greater than 0? This is obviously very simple. The probability that I need basically greater than 0 uniform 0 to 1s in order to exceed some fixed threshold is going to be 100%, right? Now let's do another case. What is the probability that n is greater than 1? So this is just basically saying, what is the probability that I need at least 2 uniform 0 to 1s in order to exceed this fixed threshold of z? So if I have my number line here and z is right here, it's saying, what is the probability that 1 is not going to be enough, right? One random variable, if I place my x1 here, I'm going to need at least 1 more to exceed this threshold. And that's basically just the same thing as saying, what is the probability that our first random variable, x1, is just going to be less than or equal to z, right? Now, 1 is a uniform random variable. It has this density up here where this height is 1 right here, right? So the probability that it's less than or equal to z is going to be all this area down here. So it's just a z by 1 box. So it is of probability equal to z, obviously. So this is just going to be z. Now let's find the probability that n is greater than 2. So the number of uniform 0 to 1s that we need is going to be at least 3. So if I have my number line here with a fixed z, it's saying when I take my first two random variables, x1 plus x2, what's the probability that basically that comes before z? And in that case, we're going to need at least 1 more to get something greater than z. So again, this right here is basically just saying, what is the probability that x1 plus x2 is going to be less than or equal to z? Now visually, this is saying, just like what we've been doing with all uniform random variables, if I have x1 on my x-axis and basically x2 on my y-axis, well, they're both uniform 0 to 1, so the probability that they're both less than or equal to this fixed value of z is just going to be everything basically under this line right here, where this is z and this is z, right? It's going to be this like little triangle here. Now the area of that triangle right there, just by looking visually, is going to be z squared divided by 2, but since we're going to keep on going with this, it's going to be less and less useful to think about this visually, because obviously we're not going to be able to visualize anything past 3 dimensions. So let's just start doing the actual integrals out. So basically what we're doing, if I have my number line here between 0 and 1, I have this fixed value of z. I'm saying x1, first of all, what's the probability that it's less than or equal to z? So basically somewhere in here. And then once I know my x1 value, I'm saying, what is the probability that x2 is basically going to be less than or equal to this difference? In that case, basically we're going to have x1 plus x2 less than or equal to z. So I'm saying for all the possible valid values that x1 can take, so between 0 and z of its density, which is just going to be 1, again, because it's a uniform 0 to 1, I'm multiplying that by the probability that x2 is less than or equal to this difference, which is just going to be z minus x1, given the fact that basically x1 is taking that value, right, and then dx1. But now if I'm given a value for x1, that's not going to change the probability of x2 because they are independent, right? So this doesn't even matter. It's just, we can just write this as basically the probability that x2 is less than or equal to z minus x1. So for some fixed value of x1 right here, z minus x1 is essentially going to be a constant. So what's the probability that a uniform 0 to 1 is less than or equal to a constant? Well, we just calculated it back here. Where instead of z back here, we have z minus x1, right? So if we plug in z minus x1 into this equation right here, we're just going to get z minus x1. So this inside here is just going to be, well, z minus x1 and then dx1 on the outside as well. Let me move that in. Now, when you do this integral right here, we're just going to get z times x1 minus x1 squared divided by 2, evaluated from z to 0. When we plug in z for x1, we just get z squared minus z squared on 2, which is going to just give us again z squared on 2. Now let's move on to the case where we have the probability of n being greater than 3. Let's keep trying to find a pattern. Well, that's just the probability that we need at least 4 0 to 1s to basically exceed this threshold of z when we sum them up. So again, this is just like saying what is the probability that the first three, x1 plus x2 plus x3, are less than or equal to z. Well, again, we can kind of do the exact same thing that we did before. We can first condition on the first uniform random variable that we put down. So let's say x1 goes right here. We integrate over all the possible values that x1 can take such that this is true, right? So from 0 to z, I take the probability of x1 occurring at that point, which has density 1, and I multiply that by basically the probability that now x2 plus x3 is going to basically be less than this difference right here, right? This difference between z and x1, where I'm integrating over all the possible values that x1 can take. And now you can see right here, when we're in here, we've basically fixed an x1 value. So this is a constant. So now you can see the recursion. Now we're calculating the probability that two uniform 0 to 1s that are independent are less than or equal to some constant, which is what we just did right here. So when we had less than or equal to z, we got basically z squared divided by 2. So now we have z minus x1. So we'll just plug in basically z minus x1 where we had in z, and then we're just going to basically get, well, z minus x1 squared divided by 2, and then that's dx1. Now, when we integrate this, we're just going to get basically negative z minus x1 cubed, and then that's going to be divided by 3 times 2, which is just going to be equal to 6. And we are integrating from z to 0, where we plug in z for x1. When we do so, we get 0 minus, and then we have this negative here, minus negative. When we plug in 0, we get z on 6. Or actually z cubed on 6, that is. So now this is just going to be equal to, well, z cubed on 6. And now the pattern is pretty clear, right? When we condition on basically what x1 is, we can just use the exact same type of formula. Probability that n is greater than 4 is just the probability that our first 4 are going to be less than or equal to z. So x1 plus x2 plus x3 plus x4 is less than or equal to z. We integrate over all the possible values that x1 can take, and then once we conditioned on a certain value for x1, we take the probability that basically x2 plus x3 plus x4 are going to be less than or equal to the difference between z and x1. And now, once we have fixed a value of x1, this becomes a constant right here, right? So we can just use the exact same equation from the step before, right? Because we have 3 uniform 0 to 1s that are independent. What's the probability that's less than or equal to some constant? Well, we just calculated that. It was basically z cubed on 6. So let's just replace the z with the z minus x1 in that equation, and we get, well, z minus x1 cubed divided by 6, and we are doing it with respect to x1. And again, when we integrate this right here, we get negative z minus x1 to the power of 4 divided by 6 times 4, so 24 from z to 0. When we plug in z for x1, we just get 0, and then when we plug in 0, we get negative basically z to the power of 4 on 24, so this is just going to end up equaling z to the power of 4 divided by 24, and now you can see the pattern. Our n value is 4. This pretty clearly is our n value, what we're raising z to the power of, and on the bottom we basically have n factorial. And you can pretty clearly show this by induction. I'm not going to do the whole thing, but I'll do the inductive step. So the probability that n is basically greater than m plus 1, let's do that. It's just going to be equal to the probability that basically the sum from, let's say, I equals 1 to n plus 1 of basically x sub I, those summed up are going to be less than or equal to z. So I condition on my x1, I'm integrating from 0 to z of that density, which is just 1. The probability that basically the sum from this time I equals 2 to basically n plus 1, my other variables of x sub I, right, they're all going to be less than or equal to z minus x1 dx1. Now I hold that it's true since we're doing induction. I hold that it's true for basically n random variables instead of n plus 1. So this right here, we can just replace that basically as, well, what's it going to be? It's going to be z minus x1 to the power of n divided by n factorial. Now this integral here is just going to be negative z minus x1, all of that to the power of n plus 1 on n plus 1 times basically n factorial, and then that's going to be evaluated from z to 0. When I plug in z, I get 0, so this is going to be 0 minus, and then I have negative basically z to the power of n plus 1. That's going to be divided by n plus 1 factorial. Then obviously the negatives cancel, and I'm just left with this value right here, which is exactly what we would expect, and it completes the induction step, right? I was trying to prove the probability that n is greater than n plus 1 when we hold basically that the term previous was true, that I get the exact same pattern, which I do. Now remember, the expected value of n was the infinite sum of all of these probabilities, right? We just found the probability that n was greater than k was just z to the power of n divided by n factorial. Now this is a very well-known limit. It's just going to be e to the power of z. And whoops, again, I just realized this problem has a typo. This should be zn as a function of z, right? Because we were using z as our basically our fixed constant. So the final answer was e to the power of z. So yeah, that was probably the hardest problem that we've done so far.